Section: Introduction. In this section, we discuss how recent advancements in foundation models have transitioned us from static language models to interactive agents capable of handling multi-step tasks in dynamic environments such as browsers, terminals, and the physical world. These agents function in closed-loop systems, where each action alters the current state and influences future interactions. To thrive in these settings, interactive agents need to plan under uncertainty and adapt to real-time failures. We explore how to create agents that excel in these interactive environments. Current post-training methods yield agents that react to immediate observations but often falter with changing or uncertain task dynamics. Techniques like supervised fine-tuning on expert demonstrations or reinforcement learning with task rewards typically train agents to choose the best action at each step. However, even with strategies that encourage longer thinking before acting, these agents remain focused on selecting the most effective action based on their internal state. This approach works well for fully observable and stable tasks but can lead to suboptimal decisions in situations where information is incomplete or conditions are changing, such as fluctuating prices during flight bookings. We argue that instead of aiming for optimal policies, agents should develop adaptive policies that can gather new information and adjust their actions accordingly. A key requirement for this adaptability is allowing agents to take more actions during deployment than those dictated by an expert's path. We propose a new aspect of test time scaling, increasing the number of interaction steps available to the agent. This gives agents the context and time needed to explore different behaviors. For instance, in a hotel booking scenario, an agent should first browse multiple listings to compare reviews and check availability before making a choice. Our concept of interaction scaling is distinct from existing methods that focus on deeper reasoning per step, as it emphasizes the importance of gathering information from the environment. An agent that only reasons about one hotel without further exploration may overlook better options that arise later. While the idea of interaction scaling is straightforward, applying it in practice and teaching agents to scale their interactions autonomously presents challenges. Without proper training signals, agents might engage in unproductive exploratory behaviors, like randomly clicking links, without progressing toward their goals. To address this, we suggest combining online reinforcement learning with a curriculum that guides how to expand the interaction horizon, enabling agents to first learn effective exploitation before exploring. We implement our approach in the domain of web agents, which is a relevant setting with established benchmarks. We demonstrate that prompting agents to think and act again after deciding to stop can improve task success rates significantly. While this increases the length of interactions and the number of tokens generated, traditional methods that extend thinking time yield minimal gains. We then advance beyond simple prompting to develop test time interaction, TTI, a curriculum-based reinforcement learning method that trains agents to adaptively scale their interactions by gradually increasing the rollout horizon. We apply TTI to large and diverse training sets, achieving state-of-the-art performance among open-source agents. Our analysis shows that curriculum training fosters adaptive exploration, allowing agents to initiate new searches or backtrack in complex tasks while efficiently navigating simpler ones. In summary, we introduce interaction scaling as a new dimension for enhancing agent performance during test time. We propose TTI to dynamically adjust the interaction horizon, and our results indicate that TTI leads to significant improvements, suggesting promising applications beyond web navigation. Section Summary. In this section, we discuss the transition from static language models to interactive agents capable of performing multi-step tasks in dynamic environments, emphasizing the need for these agents to adopt adaptive policies that allow for real-time information gathering and decision-making. We propose a novel approach called Test Time Interaction, TTI, which enhances agent performance by dynamically scaling interaction horizons, enabling agents to explore and adapt their behavior effectively, thus improving task success rates significantly compared to traditional methods. Section: Problem Setup. In this section, we consider solving a web task as a decision-making process that unfolds over a set period, driven by a reward goal. Our environment uses a transition function that changes over time and provides us with an observation at each step, reflecting the current state of the task. The agent's policy is based on a multimodal foundation model that connects the history of observations and actions to determine the next action. This history allows the policy to exhibit complex behaviors through interaction. We define the maximum number of interaction steps allowed as the environment horizon. The interaction ends when the agent either signals to stop or reaches this limit. The agent earns a reward of 1 for successfully completing the task and 0 otherwise. For our observation space, we include the task goal, the URL, and a structured view of the current web page, which features an accessibility tree and a screenshot with identifiers for each interactive element. Although the agent can access all past observations, we limit the observation history to the last 3 steps to manage context effectively, while it retains access to all past actions. We set up a discrete action space with 6 possible actions: click, type, scroll, go back, search, and stop the task with an answer. We avoid complex actions to maintain performance. To explore scaling test time interactions, we note that previous methods typically focused on increasing the number of thinking tokens at each step, which does not allow for longer interactions with the environment. We hypothesize that increasing the maximum number of interaction steps will enable the agent to use more sophisticated strategies, such as retrying or backtracking. We will test this idea through controlled experiments on Web Arena, which allows for reproducible interactions across various domains. In our experiments, we randomly select 62 tasks for testing and keep 750 for online training, ensuring a generous test time limit to allow for sufficient interaction. We use a simple prompting-based agent that observes the web page and outputs actions without relying on external modules, ensuring that any performance improvements stem solely from increased interaction steps. We find that prompting the agent to generate a reasoning trace before acting significantly improves the task success rate compared to direct action generation. We adopt a simple chain-of-thought approach as our default strategy for these experiments. To further investigate the impact of scaling test time interactions, we introduce a check again mechanism, prompting the agent to reconsider its decisions after signaling task completion. This rechecking can be extended to multiple passes, and we observe that it not only increases the length of interactions but also improves success rates across most domains. When prompted to recheck, the agent may either confirm its previous decision or revise it upon reflection. We note that it changes its action a significant percentage of the time after double-checking, indicating that with enough time, the agent is likely to explore alternatives before finalizing an answer. However, we also recognize that excessive prompting can lead to confusion, resulting in incorrect revisions of previously correct answers. This limitation highlights the challenges of relying solely on prompting to scale test time interactions, which we will address through explicit training of the agents. Section Summary. In this section, we outline our approach to solving web tasks as a sequential decision-making process, where an agent uses a multimodal foundation model to interact with a structured observation space and a discrete action space. We explore the impact of scaling test time interactions through controlled experiments, demonstrating that prompting the agent to reconsider its decisions can enhance task success rates, although excessive rechecking may lead to confusion and errors. Section: Scaling test time interaction versus per-step test time compute. In this section, we examine the impact of scaling interaction versus scaling reasoning per step. We want to determine if agents should focus on having more interaction steps or on generating longer reasoning traces at each step, given a fixed token budget. To investigate this, we analyze 2 common methods for scaling test time compute. First, we implement a strategy called per-step budget forcing. Here, we prompt the agent to wait and think again after it generates an initial chain of thought, encouraging it to reason more before taking action. We test this by varying the number of forced waits from 1 to 4. However, despite our efforts to prompt longer thinking, the agent only changes its actions 15% of the time, mostly by rearranging subtasks rather than exploring new options or correcting errors. Next, we use a method called per step best of 4, where we sample 18 candidate actions at each step and choose one based on majority voting. We refrain from increasing this further because it becomes too compute-intensive for multi-step tasks, and we notice diminishing returns from sampling more actions, even after adjusting parameters like temperature. Our first finding is that gaining new information through interaction is more beneficial than simply thinking longer at a single step. We plot task success against total compute, measured in tokens per trajectory. Among the strategies, interaction scaling shows the best results, achieving the highest success rate as the token budget increases. Budget forcing provides moderate improvements but levels off, while best of 4 yields the least benefit, indicating that repeatedly sampling actions is not the best use of compute in interactive tasks. This leads us to consider how to allocate a limited compute budget between more interaction steps and longer reasoning. We illustrate how scaling interaction steps and tokens per step affects performance and total tokens. Our analysis shows that scaling interaction steps is more effective than scaling reasoning within steps, particularly in tasks that allow for gathering new information. Our second finding is that simply prompting the agent is not enough for effective interaction scaling. The check again strategy only allows the agent to reassess its behavior after completing a task, limiting its ability to switch between exploration and exploitation during a rollout. We also tried combining interaction scaling with budget forcing and best of 4, but merely increasing compute through prompting did not lead to better outcomes. In fact, excessive prompting can confuse the agent and hurt performance. To move beyond prompting, we explore how to train agents that can effectively use interaction scaling. We consider using reinforcement learning with binary task rewards and longer task horizons. However, we face challenges in training agents to scale test time interaction. One challenge is training agents with fixed, long horizons. We can encourage agents to take more steps by training them at longer horizons. We use a simple form of reinforcement learning with binary rewards, retaining only successful trajectories and updating the agent based on high reward rollouts. This method is stable and has been effective in previous training efforts. We vary the agent's horizon during training. Smaller horizons expose the agent to more exploitative rollouts, while larger ones include exploratory rollouts. Our findings show that agents trained with smaller horizons learn quickly but tend to overfit, while those trained at longer horizons learn more slowly due to higher variance and credit assignment challenges. We observe that agents trained at longer horizons associate exploratory actions with high rewards initially, but noisy credit assignment slows their learning. The effectiveness of horizon length varies by domain. In complex environments, long horizon agents perform better, while in simpler settings, the differences are minimal. We also note that the total tokens generated per action slightly decrease during training, indicating that the training does not directly encourage longer reasoning. Ultimately, our observations suggest that simply setting a long horizon is not enough to reliably scale test time interaction. This motivates our core idea. Instead of fixing the horizon, we aim to dynamically scale the interaction length during training. Section Summary. In this section, we investigate whether agents should prioritize more interaction steps or longer reasoning traces during test time compute scaling. Our findings indicate that increasing interaction steps is more effective for task success than extending reasoning per step, and we highlight the challenges of training agents to optimize interaction scaling, suggesting a dynamic approach to scaling interaction length rather than fixing it. Section. Our approach. Curriculum over interaction horizon. In this section, we propose our approach called TTI, or Test Time Interaction, which is a curriculum-based online reinforcement learning method. We start by training the agent with short task sequences and gradually introduce longer ones. Unlike traditional curriculum learning methods that focus on easier tasks first and often depend on predefined rules, we define our curriculum based on the maximum number of steps the agent can take in each task. This way, we avoid needing explicit measures of task difficulty. Our curriculum design aims for the agent to first master basic skills to handle simpler tasks before moving on to more complex ones through skill chaining and exploration. We explored two strategies, one that increases the maximum steps allowed gradually, giving the agent time to solidify its skills, and another that increases the steps more rapidly, assuming the agent can quickly learn the basics and benefit from early exploration. We implemented these strategies in Web Arena, using non-test tasks for online training. We set specific parameters for our experiments and found that the multiplicative approach outperformed the additive one. This is likely because it allows the agent to engage with longer tasks sooner, helping it avoid overfitting to shortcuts. Our findings led us to adopt the multiplicative curriculum as the standard for TTI. Next, we evaluated TTI in large-scale, realistic environments. To facilitate extensive training without using the benchmark directly, we generated synthetic tasks inspired by previous work. We also used an exploratory agent to interact with websites and create diverse tasks. For evaluation, we employed a verifier that labels task outcomes with high accuracy. We trained separate agents for different benchmarks to prevent contamination from synthetic data. Using a specific model, we sampled tasks and updated our training based on successful interactions. We compared our approach against various models, including those using fixed horizons and other well-known agents. Our results show that the TTI-trained model achieved a high task success rate, setting a new standard among open agents trained solely on public data. While other methods relied on private data, our approach demonstrated the effectiveness of synthetic data generated by our model. We also found that TTI outperformed fixed horizon methods, particularly in domains that benefit from extended exploration. To understand how TTI enhances exploration, we measured the agent's actions during training. We observed that as the maximum allowed steps increased, the agent's ability to explore effectively also improved. In contrast, runs with fewer steps showed a decline in exploration capabilities. Our analysis indicates that TTI helps the agent balance interaction and reasoning, leading to better performance without overthinking. Section Summary. In this section, we propose TTI, Test Time Interaction, a curriculum-based online reinforcement learning approach that gradually increases the interaction length for agents, allowing them to first master basic skills before tackling more complex tasks. Our empirical results demonstrate that a multiplicative curriculum outperforms an additive one, leading to improved task success rates and effective exploration strategies in large-scale environments. Section: Case Studies, Strengths and Failure Modes. In this section, we conduct detailed case studies to examine how TTI performs across different tasks and domains. These studies reveal both the strengths and limitations of our approach. One strength is our effective exploration in complex tasks. For example, when tasked with finding the baking temperature for a highly rated apple pie recipe, our agent initially selects a recipe but encounters an issue it cannot resolve. It then tries another recipe but fails to find the temperature. Eventually, it returns to the list and successfully identifies a suitable recipe. We notice that this exploratory behavior develops over time. Early in training, the agent tends to stick with the first recipe it finds, but as training progresses, it learns to explore and backtrack. This shows that by varying the interaction length during training, we help agents learn to adapt their exploration strategies. Another strength is our strategic exploitation in simpler tasks. For straightforward tasks, like filling out forms or looking up information, the TTI agent efficiently completes tasks without unnecessary exploration. For instance, when asked to find the top trending open source project on GitHub, the agent quickly navigates to the relevant section and performs a search, demonstrating a good balance between exploration and exploitation based on the task context. However, we also identify some failure modes that indicate areas for improvement. One issue is the agent's over-reliance on resets. When an action fails, it often resets the task instead of trying to recover within the current context. This suggests that the agent defaults to searching rather than using more effective domain-specific actions. We also see repeated resets during the same task, indicating a lack of adaptive error recovery. We believe that enhancing TTI with structured exploration and using dense rewards or multi-turn reinforcement learning could help address this. Another failure mode is limited self-verification. The agent sometimes fails to check its actions against the task requirements, particularly at the final step. For example, it might identify a repository from 2021 when the task requires one from 2022, acknowledging the mismatch but still accepting the incorrect answer. This points to a need for improved reasoning at each step, which we aim to enhance in future iterations. Next, we assess TTI on the full web arena, using a prompting-based verifier for training and original evaluators for assessment. Our results show that TTI outperforms other open-source agents trained solely through self-improvement on self-generated data. While TTI improves over the zero-shot baseline, the gains are smaller than expected, likely due to the complexity of web arena tasks and occasional actions that are valid in real-world scenarios but not in web arena. We also explore the potential for further scaling. Although TTI allows agents to adjust their interaction horizon, we question whether we can enhance performance by combining TTI with inference time interaction scaling techniques. To investigate this, we apply a check again strategy to intermediate TTI checkpoints. Our findings indicate that this rechecking improves task success, especially in the early training stages when agents are more prone to premature termination. Even in later stages, rechecking continues to provide modest performance gains, acting as a safety check for well-trained agents.